Now we will see how to solve system of equations. So a system of equation that you're familiar with is a 2 by 2 system of equation that you have learned before. Okay, so system of equations, if it's a 2 by 2 system of linear equations, we can simply solve it by elimination or substitution. But what if the order increases to 3 by 3, 4 by 4, 5 by 5, and so on? Okay. So to solve a higher order matrices, even 3 by 3 system of equation, you need to use matrices method. Okay, so the method that is related to matrices would be elementary row operation, right? So for example, if you have a matrix of with A, B, C, D, this is a 2 by 2 matrix. It has got 2 rows and 2 columns. And row 1 has AB, row 2 has CD. So this is called a system of equation. For example, if we have matrix A with 2, 4, 1, 5, this is equated to A1, 1, 1, 2, 2, 1, and 2, 2 respectively. It means it shows that each element is labeled with A1, 1 here means row 1, column 1 represents 2. And A22 here means row 2, column 2, so it represents the element 5. So Aij refers to I row and j column. So I've introduced this in the earlier slides. Okay, this is just a recap on what does a system of equations actually means. For example, if we have a system of equation which is 2 by 2, so in this case, this system of equation has got two unknowns x and y. So it's called a 2 by 2 system of equation, and we can write it in augmented form. So this is how we write it in augmented form, right? We write the coefficients of x, 2 and 1, and coefficients of y, which is 4 and 5. And the left hand side, the right hand side is actually the values of this 42 and 57, what the first and second equation equals to. So this is how we write the augmented form. The dotted line is as if it represents x and y, and then you need to perform elementary row operation to solve the system. Okay. So elementary row operation in for 2 by 2 system, um, in order to solve it, you need to make the value of 1 here 0. So in order to do that, uh, again, you represent your first row as row 1, and your second row as row 2. Okay, so it will be 2 of 2 times 1 minus 2. Okay, so it will be equal to 2 of row 2, take away row 1. So 2 minus 2 would be a 0. And the other elements follow through the same operation for second row. So it will be 5 times 2 minus 4. So 10 minus 4 is 6. And then 57 times 2 minus 42, you will get a 72. Okay, and then the first row, you need to divide the first row with 2 simply because you need to make the left hand corner always as 1 in order to solve system of equations. So you divide the whole row with 2. So when you divide the whole row with 2, you will get 1, 2, and 21. And in this case, 6y here equals to 72 from the second row. You can solve your y, and then you can move up to the first row and solve your x plus 24 equals to 21. You can solve your first row. So solving your first row will actually give you x is negative 3. So it looks a bit complicated, but elementary row operation, it's useful to solve system of equations with higher order like 4 by 4, 3 by 3, 4 by 4, 5 by 5. But for our learning outcome here, we will focus on how to solve system of equation for 2 by 2 and 3 by 3. So for 3 by 3 system, you can use the following strategy. You need to use again elementary row operation to reduce this matrix to this form. Okay, this is specifically to solve it, yeah. So you need a triangle of zeros, okay, the left hand corner. So in order to get that lower half under the leading diagonal of a 0, you need to you need to solve it using elementary row operations. So for example, if you need to solve the system of equation as shown on the screen. Okay, right, first you need to write it in augmented form. That will be the first step. So when you copy the system of equation into an augmented form, please copy all the unknowns very carefully, all the coefficients of x, y, z, and please consider the negative and positive values as well. So you convert your system of equation into the augmented form. That will be the first step. Next step would be you need to actually this is row 1, will be row 2, this will be row 3. Okay, so now you need to get a triangle of 0 here. Okay, to get a triangle of 0 there, you normally start off with your third and your second row. So in this case, in order to make the value of 1, 0 over here, it will be 1 minus 1 at the first row. So it's as simple as row 3 minus row 1, the first step. 3 minus row 1. So when you minus, the others follow through the same operation. All right. So 1 minus 1, negative 1 minus 1, so you get negative 2. Okay, and then 1 minus 1 as well, so you get a 0, and then 4 minus 2, you get a 2. So the operation of the row 3 follows for the other elements as well. And then next, you're trying to make the 4 a 0. So to make the 4 a 0, it will be row 2, which is 4 minus 4 times 1. So it's row 2 minus 4 row 1. Right? Row 2 minus 4 row 1. And the other elements of the second row will follow the same operation respectively. So 4 minus 4 times 1 is a 0. And then next, 2 minus 4 times 1, 4. So 2 minus 4 is negative 2. 1 minus 4 times 1. So 1 minus 4 is negative 3. 4 minus 4 times 2, 8. So 4 minus 8 would be negative 4. So this is how you get the second row. Okay. The top row, just make sure the left hand corner is always a 1. Okay. Once you have got that, now there's a next step where you actually need to zero your negative 2. Convert this to a 0. So in order to convert that, to avoid the zeros of row 2 and row 3 to be changed, when you want to 0 negative 2, just involve row 2 and row 3. Okay, so for example, it will be row 3 minus row 2. So it's negative 2 minus negative 2. It will be negative 2 plus 2, and you will actually get a 0 for your actually 0 the negative 2. And the other values on the same row must follow the same operation. So it will be 0 minus 0, negative 2 minus negative 2, you get a 0, and then 0 minus negative 3, you get a 3, and 2 minus negative 4, 2 plus 4, you get a 6. Okay, so in this case, then you've got the triangle of form. Okay, and you can always multiply any row with a negative value. So if you multiply negative 1 to the second row, you will actually get a positive value throughout. You will positive all the elements. You can do that. The step is not really necessary. Right? If you want to do that, it's an optional. So next, for row 3, based on, always start off when you want to solve after you get the triangle of zeros. Okay, you need to solve your x, y, z, because that's the goal. You need to solve the equation. So this row, first row is coefficient of x, second row is coefficient of y, the third row is coefficient of z. So in this case, 3z should equal to 6. So z will be 2. Okay, then you move on to second row. 2y plus 3z, right, equals to 4. So 2y plus 3z, 3z is 6, right? 3 times 2 is 6 equals to 4. And you solve your y. And you move on to first row, x minus 1, sorry, x plus 1, x plus y plus z equals to 2. Right? X plus y plus z, so y is negative 1, z is 2 equals to 2. You will solve your x as 1. So the solution is x1, y is negative 1, and z is actually 2. So now, for example, if you have, when you solve using elementary row operation, there are scenarios where you don't have a solution. There are scenarios where you actually, solutions are undefined, or the solutions are infinitely many. Right? And there's also a scenario, the normal scenario, when you solve your xyz, that is called a unique solution, right? So there are 3 different scenarios here. So the one that we have solved in our previous slide, which is getting us x, y, z value respectively, that refers to a system that has unique solutions. So now we will look at how system has redundancy or inconsistency. Okay, so for example, if you have a matrix like that and you perform elementary row operation, okay, by changing it to an augmented form, then you perform elementary row operation trying to get a triangular of 0, right, in the left hand corner. So in this case, while trying to get the triangle of zeros, over here, you actually get a whole row of zeros. If you observe over here, so when you get a whole row of zeros and you try to solve, it will be like 0z equals to 0. When you try to solve this, it tells you that the system is actually redundant. When you get a whole row of zeros, the system is actually redundant. So there is no unique solution. Unique solution means it has x, y, z solution to this system. Right? In fact, this is actually a system. So a redundant system of equation actually has infinitely many number of solutions. So it doesn't have unique solution, but it will have infinitely many solutions. So how are we going to write out the solutions? So for example, the row tree is not going to give you any values, so you ignore row tree and you actually move on to row 2. So when you move on to row 2, over here is this. So the row 2 actually gives you negative 3y plus z equals to negative 3. Right? So next you need to write this in the form of a infinitely many solutions form. So in this case, you need to get y in terms of z. Okay, once you get y in terms of z, you can move on to the first row, which is x plus 2y plus 2z equals to 11. So x plus 2y plus 2z equals to 11. Okay, this is substituted y equals to z plus 3 over 3 is substituted into row 1. Okay, so we should simplify x in terms of z. Right? So you will get x, y, and z in terms of z. Okay, so once you get x, y, z in terms of z, this system has infinitely many solutions because each time you assign a z value. So for example, when z is actually 1, okay, you will get a set of solutions. So when z is 1, z would be 1, okay, and then your y would be 4 over 3, and then your x would be 27 minus 8 over 3 lah. Okay, so you will get a respective x, y, z value depending on the z value assigned. So a particular solution for this system can be found by assigning a value to z. So when z is 1, it has one set of solution. When z is 2, it has another set of solution. That's why when you get a whole row of 0 while doing elementary row operation, you will get a system which is redundant and a system which has infinitely many solutions. And now we will look at a system that has no solutions at all. So for example, if you have an elementary rule, you perform an elementary rule operation for a system of equation given as over here, alright? So you're writing the augmented form, you perform the elementary row operation with the intention to get a triangle of zeros. Okay, you need to get a triangle of zeros here. Okay, so in the process of getting the triangle of zeros, you will get a triangle of zeros, of course, and then you get a row of zeros with a number over here. Okay, so this kind of outcome of elementary row operation actually means that the system has no equation. Okay, the proof is over here. So when you try to solve this, row 3 suggests that 0z equals to -1, which means 0 equals to -1, which tells us that the system is not consistent or inconsistent, and there are no solutions that exist for this particular system of equation.